Hey, it's Weinstein, and today we'll discover how the silent flight of owls inspired quieter drones, fans, and wind turbines. A mouse in a dark field hears everything. Every rustle, every snap twig, every wing beat, that's how it stays alive. And then, out of the blackness above, something arrives that it never heard coming, not 1 second before, not half a second before, nothing. An owl flies in near total silence. And right now, engineers are desperate to steal that trick for our drones and our wind turbines. Owls are big birds. Broad wings, a heavy body, powerful strokes by every rule of physics that should make noise. Push that much air around and you should hear it. Yet many owls fly so quietly that a human standing a few meters away hears essentially nothing. Not muffled, not faint, effectively silent. And that silence isn't luck. It's engineering, feather by feather. And the owl has a very good reason to be quiet. Its prey, mice, voles, shrews have superb hearing. They live their whole lives listening for danger, and a rodent that hears wing beats simply bolts. So for an owl, sound isn't just inconvenience, it's the difference between eating and starving. Every decibel it makes gives its dinner a head start. Evolution had no choice but to solve this. There's a second reason, and it's easy to miss. Owls hunt largely by ear, pinpointing the tiny scratching sounds of a mouse under leaves or even under snow. Now imagine trying to listen for a faint rustle while your own wings roar next to your head. Your own noise would drown out the thing you're hunting. So silence doesn't just hide the owl, it lets the owl hear. Quiet is both weapon and scent. So where does the sound of flying actually come from? Not from the muscles or the bones. It comes from the air. Any wing, blade, or propeller moving through air pushes it, drags it, and stirs it up. The air doesn't flow past smoothly and quietly, it swirls, tumbles, and slams back together. Those churning motions are pressure changes in the air. And pressure changes rippling outward is exactly what sound is. Keep that in mind, because it's the whole story. Sound is nothing more than tiny, rapid changes in air pressure that travel to your ear. A drum makes them by punching the air. A speaker makes them by vibrating, and a wing makes them by churning the air into chaotic swirls that push and pull on the air around them. Any disturbance in the air becomes a sound. So flying quietly means disturbing the air gently. The specific villain here has a name: turbulence. When air flows smoothly in neat parallel layers, it's calm and quiet. But push it too hard, or around an awkward shape, and it breaks up into chaotic, tumbling swirls, eddies of all sizes, crashing into each other. That chaos is turbulence, and turbulence is loud. Every blade, propeller, and wing makes it. The engineering question is what you do about it. And there's one place on any wing where noise is generated most fiercely: the trailing edge, the back edge where the air finally leaves. Air has traveled over the top surface and along the bottom at different speeds, and at that back edge, they meet again abruptly. That collision, right at a sharp edge, is where a huge amount of flight noise is born. Get that edge wrong, and you get a wing that hisses and roars. Here's the intuition. Imagine two crowds of people walking at different speeds, suddenly forced to merge at a hard barrier. You get shoving, chaos, noise. Now imagine they merge gradually along a long diagonal, much calmer. Air behaves the same way. When turbulent air is forced past a sharp edge all at once, its swirls get converted efficiently into sound waves. The sharper and more abrupt the edge, the louder the conversion. Now, what makes the owl remarkable isn't one clever fix. It's that it stacks three completely different mechanisms on top of each other, each attacking noise at a different stage of the airflow. One at the front of the wing, one at the back, and one across the whole surface. Together, they take a big, air-pushing wing and make it whisper. Let's take them one at a time. Start at the front. On the leading edge of an owl's wing, the edge that meets the oncoming air first, the feathers carry a row of tiny stiff hooks, like the teeth of a comb. Look at almost any other bird and that edge is smooth. On an owl, it's serrated. That comb is the first line of defense, and it starts working before the air has even traveled across the wing. Without it, air arrives at the wing as one big, unified flow. That single stream builds up into large, powerful swirls as it moves over the surface, and big swirls make big noise. The comb breaks that unified flow into many small streams as it arrives. Instead of one huge eddy, you get a crowd of tiny ones. And that changes the sound completely. Because with turbulence, size matters enormously. One big, coherent swirl pushes on a lot of air at once and radiates a strong, low sound, the kind that carries. Many tiny swirls each push very little, and crucially, they're disorganized. They push and pull in different directions at different moments, partly canceling each other out. The comb doesn't remove the turbulence, it shatters it into pieces too small and too jumbled to be loud. Think of a stadium crowd. 50,000 people all chanting the same word in unison is deafening a single unified wave of sound. 50,000 people, each muttering something different, is just a murmur, even though the same number of mouths are moving. The comb turns the roar of an organized crowd into an unintelligible mumble. Same air, same energy, far less noise. Now to the back of the wing, where we said noise is born most fiercely. On an owl, the trailing edge isn't a clean, sharp line. Each feather ends in a soft, flexible, fringe, loose, hair-like filaments that trail off into the air like the frayed end of a rope. Where other birds have a crisp edge, the owl has something closer to a soft brush. And that softness solves the merging problem. Remember the two crowds slamming together at a hard barrier? The fringe removes the barrier. Instead of the upper and lower airflows colliding abruptly at a sharp line, they mingle gradually through those flexible filaments. The merge becomes gentle and spread out instead of sudden and violent. Less abrupt collision means dramatically less noise generated. There's another way to see it. A sharp trailing edge is very good at converting turbulence into sound. It's an efficient loudspeaker for chaotic air. A soft, porous, flexible fringe is a terrible loudspeaker. The swirls pass through it, get broken up and smeared out, and never get that clean, hard surface to push against. The owl didn't reduce the turbulence there. It removed the thing that was turning it into sound. And now the third mechanism, spread over the entire wing. Run a finger over an owl's feather, and it doesn't feel like a normal bird's. It's soft, genuinely velvety, covered in a fine, plush layer of tiny structures. Other birds have smooth, slick feathers built for speed. The owl is wearing what amounts to a coat of acoustic velvet, and it works in two ways at once. First, the plush surface stops the wing from being an acoustic mirror. Sound waves that hit a hard, smooth surface bounce off cleanly, the same waves hitting a soft, fibrous one get trapped in the fibers and absorbed. It's the same reason a recording studio has soft foam on the walls and a bathroom echoes. The velvet soaks up the residual sound that the other two tricks didn't eliminate. And there's a second, subtler job. An owl's wings brush against each other and against its body in flight. On a normal bird, feather rubbing on feather makes a distinct rustling sound a giveaway. The soft velvet surface makes that contact quiet, the way a suede sleeve is quieter than a nylon one. It hushes the wing's own housekeeping noise as well as the air. So put it together. The comb at the front shatters the incoming flow into harmless little swirls before they can grow. The fringe at the back lets the flows merge gently instead of slamming together at a hard edge. And the velvet across the surface absorbs whatever sound survives the first two: prevent, soften, absorb. Three independent solutions working on the same problem at three different stages. And that stacking is the real lesson. No single trick is enough. The noise has multiple sources, so it needs multiple fixes. Attack it at the leading edge, again at the trailing edge, and once more at the surface and the reductions compound. It's a defense in depth. Any one mechanism alone would give you a somewhat quieter bird. All three together give you a bird you cannot hear. And here's an honest detail that makes the story better. This silence isn't free. That soft, fringed, velvety wing is aerodynamically less efficient than a sleek, smooth one. The owl trades away some speed and efficiency to buy quiet. That's why fast-flying birds don't have it for a falcon, in a dive, speed is everything, and noise doesn't matter. Silence is a deliberate trade, and the owl made it. Now, people have known owls were quiet for a very long time. The hard part was explaining precisely how, in the language of physics, which mechanism does what and how much each contributes. That's the work of a field called aeroacoustics, the study of how moving air creates sound. And in 2020, two researchers published the definitive account of what an owl's wing is actually doing. Justin Jaworski and Nigel Peake published a review titled Aeroacoustics of Silent Owl Flight in the Annual Review of Fluid Mechanics. They pulled together decades of measurements, wind tunnel tests, and theory to lay out how the serrations, the fringe, and the velvet each suppress sound. It turned a beautiful natural history fact into something engineers could actually calculate with. And once you can calculate it, you can build it. That's the crucial step. Owl feathers are fuzzy, so it's quieter, isn't something you can put in a design. But a porous, compliant trailing edge reduces noise radiation by this much in this frequency range. That's an engineering specification. Jaworski and Peake gave the field the physics to design with, not just admire. The owl stopped being a curiosity and became a blueprint. And we needed that blueprint because we have a noise problem. We filled the world with spinning blades, fans, propellers, turbines, rotors. Every one of them is a wing doing exactly what the owl's wing does, pushing air, making turbulence, generating sound. And unlike the owl, ours are loud. That noise has become a real constraint on where we're allowed to put our technology. And noise is a genuinely underrated problem. It's not just annoying. Chronic noise exposure is linked to sleep disruption, stress, and cardiovascular strain. It's treated as a public health issue, not a nuisance. It shapes law. There are limits on how loud things can be near where people live, which means noise doesn't just bother us. It actively blocks technology from being deployed. Nowhere is that clearer than wind power. A wind turbine's blade is an enormous wing sweeping through the air at high speed at its tip, and it's noisy, that characteristic swooshing pulse. That sound is precisely the trailing edge noise we've been talking about, generated at industrial scale, day and night, right where the wind is best. And that noise carries a real cost. Turbines must be sited far enough from homes to stay under legal noise limit. That means the best windy sites near towns are often off the table, projects get blocked by objections, or operators have to slow the blades at night, deliberately generating less electricity to stay quiet. Noise isn't a side issue for wind power. It directly limits how much clean energy we can actually harvest. So engineers went to the owl. Wind turbine blades are now being built with serrated, trailing edges, rows of cone-like teeth along the back edge, doing exactly what the owl's fringe does, letting the airflows merge gradually instead of colliding at a hard line. You can see them on modern turbines, a jagged sawtooth strip running along the blade. That's not decoration, that's an owl feather, scaled up to 20 meters. And it works. Serrated edges measurably cut the noise a blade makes, and the payoff is bigger than it sounds. A quieter turbine can be sited closer to where people live and where the grid already is. It can run at full speed at night instead of being throttled. It can win planning permission that a louder machine would lose. Copying an owl doesn't just reduce annoyance, it lets us build more clean power. Then there's the everyday end of the spectrum, fans. Your laptop, your desktop, your game console, your fridge, the ventilation in your office, all of them move air with spinning blades, and all of them make that same trailing edge noise. The whine of a fan spinning up is turbulence being converted into sound, right at the edge of each blade. It's the owl's problem, in miniature, on your desk. So fan blades are being designed with serrated and fringed edges borrowed straight from owl wings. Quieter computers, quieter appliances, quieter ventilation, and it matters more than comfort. In data centers, cooling fans run by the thousand around the clock. In hospitals, ward noise affects patient sleep and recovery. A few decibels off every blade, multiplied across all of it, is a meaningfully quieter world. And then there's the one everyone notices, drones. That distinctive, aggressive buzz is the sound of small propellers spinning very fast, churning air into turbulence. It's the reason a single drone can dominate a quiet park, and the reason large-scale drone delivery over cities is a genuinely contentious idea. Nobody wants 100 angry mechanical hornets over their neighborhood at 7 in the morning. So drone noise isn't a minor complaint, it's one of the main obstacles to drones being widely accepted in cities. Delivery, inspection, emergency response, all of it depends on drones being tolerable to live near. And in military and conservation uses, quiet is the entire point an unheard drone can observe without disturbing wildlife or alerting anyone. Owl-inspired serrated and fringed rotor blades are being developed for exactly this. Stop and take in the range. The same physics break the flow into small swirls, soften the trailing edge, absorb what's left works on a wing that hunts mice at night, on a rotor the size of your palm, on a laptop fan, and on a turbine blade longer than a tennis court. From a silent hunter to a wind farm. The air doesn't care about scale. It responds to the same tricks every time. And notice how the owl achieves it. Not with more powerful muscles, not with some exotic feather material, and not by flying slower. It's pure structure. The shape of an edge, the flexibility of a fringe, the texture of a surface. Details you'd need to look closely to even notice. Once again, the breakthrough isn't in the raw material or the raw power, it's in the fine geometry of the surface. Now, honestly, our copies are not as good as the original. Serrated edges reduce turbine and fan noise measurably, but they don't make a turbine silent the way an owl is silent. We're mostly copying one of the three mechanisms, the trailing edge, because it's the easiest to manufacture. Reproducing a velvety, sound-absorbing surface that survives rain, ice, and grit for 20 years is a much harder problem. And remember, the owl's own trade-off. Quiet costs efficiency. The same applies to us. Add serrations to a blade and you may lose a little aerodynamic performance, so engineers tune the design for the best balance of noise and output. There's no free silence for owls or for turbine. The engineering work is finding the sweet spot for each application, and that work is ongoing right now. And that's normal. The owl wasn't designing wind turbines, it was trying to catch mice without being heard. Our job is to recognize the mechanisms in its wing and adapt them to machines it never imagined under conditions it never faced. The physics of the serrated edge and the porous fringe is genuinely priceless. Engineering it into a 20-meter blade that lasts decades is our part of the work. So what did we actually take from the owl? Not feathers, and not biology. We took 3 physical mechanisms. Break the incoming flow into small disorganized swirls, let the flows merge gradually through a soft, porous edge instead of colliding at a sharp one, and absorb residual sound with a textured surface. Those ideas are now on turbine blades, fan blades, and drone rotors, a hunting strategy from a dark field, turned into infrastructure. So the owl turns out to be a superb acoustic engineer. It solved a problem we're still wrestling with, how to move a lot of air without making a sound, and solved it with nothing but the shape and texture of its surfaces. And it was doing this long before we built our first propeller. Once again, nature got there first, out in the dark, working in complete silence. There's something poetic here. The owl's greatest achievement is something you can only experience as an absence. You don't hear it. There's nothing to point at, nothing to be impressed by in the moment. The whole triumph is that nothing happens. Some of the finest engineering in nature and in our own machines is exactly like this. Invisible, inaudible, and noticed only when it fails. And think about how much noise quietly costs us. Wind farms that can't be built, turbines throttled at night, delivery drones grounded by objections, sleep lost near airports and highways. We treat sound as a minor irritant, but it shapes where we can put our technology and how well we live alongside it. Learning to be quiet isn't a luxury feature, it's what lets useful things exist near people. There's a design lesson in the owl's 3 mechanisms too. It didn't find one perfect solution, it layered 3 imperfect ones that each attack the problem at a different state. Prevent it, soften it, absorb it. That's a strategy worth borrowing far beyond acoustics. When one fix can't do the job, stack several partial ones and let their effects compound. Nature rarely relies on a single line of defense, and the honesty of the owl's trade-off is refreshing. It gave up speed and efficiency to buy silence, because for its way of hunting, silence was worth more. Engineering is always like that. You don't get everything. You choose what matters most. A falcon chose speed. An owl chose quiet. Neither is wrong. The skill is knowing which currency you're actually spending and what you're buying with it. And notice where all the action is. At the edges. The leading edge, the trailing edge, the surface texture. Not the bulk of the wing, not its size or strength, the thin boundaries where the wing meets the air. So much of how something behaves is decided in the last millimeter of its surface. It's a good reminder to look at the edges of things, not just their middles. Here's the thought to sit with. Evolution spent millions of years teaching one bird how to move through air without leaving a trace of sound purely so a mouse wouldn't hear it. And now, that same silence might be what lets us put wind farms near towns and drones over cities without making the world louder. A predator's stealth turned into a way for our machines to be better neighbors. So next time you see an owl in a photo, in a documentary, or if you're very lucky, gliding across a field at dusk, notice what you don't hear. That silence is a stack of 3 brilliant mechanisms working at once, hidden in the edges of its feathers. It kept owls fed for millions of years, and it may soon be quietly spinning above your neighborhood. Nature figured it out long ago. Our job is just to look and ask, why does this work? Oh, you're still here? Thanks for watching. All right, I'm done here. Catch you later. Yeah?